Ever notice how in those epic battle stories, there's always that, hidden weapon, the one that can just change everything and make even like the toughest warriors unstoppable? Well, in the fight against cancer, our immune system might have a secret weapon like that, something called CD122.
And just like any powerful weapon, it's not just about having it, it's knowing how to, use it strategically. CD122 is like, imagine a communication hub on certain immune cells. Is picking up these like vital orders for our body's defenses. So it's not the weapon itself, but it's playing this like crucial role in directing the whole army, if you will.
Okay, so instead of just charging in blindly, CD122 is making sure our immune cells are, locked and loaded and aiming for the right target.
Exactly. And those orders coming through CD122, they're delivered in the form of proteins called IL-2 and IL-15. Think of them as the go forth and conquer signals, telling our T cells to seek and destroy those cancerous invaders.
Okay, so CD122 is receiving these powerful signals, but how does it actually get those messages to the T cells? What's the process there?
It all comes down to this receptor complex, a sort of three-part lock that needs the right key combination to unlock the full potential of our T cells. CD122 is one of those keys, and it works together with IL-2RA and DOC. And each element is essential for recognizing and binding with IL-2 and IL-15, ultimately activating the T cell for battle.
So it's like a three-way handshake, each part vital for that solid connection. Okay, got it. But let's talk about the troops themselves. We keep mentioning T cells, but I understand there's like a special ops unit within that army, the CD8 plus T cells. What makes them such power players against cancer?
You're right, not all T cells are created equal. CD8 plus T cells are the heavy hitters, the ones directly engaging with and destroying those rogue cancer cells. And this is where CD122's role as a signal booster becomes incredibly important. By relaying those IL-2 and IL-15 messages, it directly impacts how effective these CD8 plus T cells are. We're talking increased numbers, longer lifespans, and even a boost in their attack strategy against tumor cells.
So CD122 is essentially their drill sergeant, whipping them into the ultimate cancer fighting force.
Exactly. But what's really fascinating is that IL-15, one of the proteins we discussed earlier, goes a step further. It's crucial for creating and maintaining memory T cells.
Memory T cells. So it's like having an immune system that remembers past battles and comes back even stronger.
Precisely. Imagine a group of elite soldiers who have encountered a specific enemy before. They remember the enemy's tactics, they're prepared, and they can neutralize the threat much faster. That's what memory T cells do. They provide long-term surveillance against specific cancer cells, ready to mobilize at a moment's notice.
That's incredible. So not only does CD122 help to mobilize the troops for the current battle, but it also helps to build a stronger, smarter army for the future. But I have to ask, with great power comes great responsibility, right?
Hmm.
Are there any potential downsides to, manipulating something as powerful as CD122?
It's a crucial point to consider. While the potential of CD122 is enormous, we're essentially talking about fine-tuning a delicate and complex system. Too much stimulation, and things can go off the rails. Think of it like this. You want a strong immune response, but not so strong that it starts attacking healthy tissue.
So it's all about striking that delicate balance.
Exactly. And this is where understanding the nuances of different T cell populations becomes crucial. Remember those regulatory T cells or TREGs we touched upon earlier? They act as kind of like the peacekeepers of the immune system, preventing it from going into overdrive and attacking our own bodies.
Right, like the diplomats making sure things don't escalate into a full-blown war.
Exactly. And while their role is essential in preventing autoimmune reactions, when it comes to battling cancer, we kind of need our killer T cells to have the upper hand. It's like trying to win a war with one hand tied behind your back if the TREGs are overly active.
So the challenge then becomes, how do we target those killer T cells through CD122 without accidentally boosting the TREGs and, basically dampening the anti-cancer response?
Precisely. It's about precision targeting, making sure our secret weapon is aimed at the right enemy. And that's where things get even more interesting. One promising avenue involves something called monoclonal antibodies. Imagine these as tiny, highly targeted missiles, each programmed to seek out and bind to a specific target in the body.
And in this case, the target we're interested in is CD122.
Exactly. One monoclonal antibody that's showing a lot of promise is called TM1. And here's where it gets really interesting. TM1 isn't a one-trick pony. Depending on how it's designed and administered, it can either enhance or block CD122 signals.
Wait, hold on. So it's like a light switch that can turn the lights both on A and D off at the same time? How does that even work?
It's less about a simple on-off switch and more like a dimmer switch. We can fine-tune the level of immune activation depending on what's needed. TM1 achieves this by interacting with CD122 in a very specific way. In some instances, it amplifies the signals coming from IL-2 and IL-15, supercharging those T-cell responses. But in other cases, it can effectively block those same signals, calming down an overzealous immune response. This incredible versatility opens up therapeutic avenues not just for cancer, but also for autoimmune diseases where dampening the immune response is key.
So in a sense, we're talking about a universal remote control for the immune system. We can crank up the dial on those killer T cells when we're fighting cancer, and then dial it back down when we need to calm things down in autoimmune diseases.
That's a great way to put it. And it highlights just how complex and interconnected the immune system really is.
We've talked about TM1's potential in both cancer and autoimmune diseases, but what does the future hold for CD122 targeted therapies more broadly? Is this just the tip of the iceberg?
I'd say we're just scratching the surface. Researchers are constantly exploring new ways to make these therapies even more targeted and effective. Imagine, like, engineering even more sophisticated antibodies, ones that act like double-headed missiles, or even employing microscopic delivery systems that transport medication directly to the heart of a tumor.
Okay, that sounds straight out of a science fiction movie.
I know, right? But these advancements are rapidly becoming a reality. In the next part of our deep dive, we'll delve into these cutting-edge technologies and explore how they're pushing the boundaries of what's possible with immunotherapy. You don't want to miss it.
So last time we were talking about those monoclonal antibodies, and I was picturing them kind of like, a seek and destroy missile system for our immune cells.
Right. Very targeted.
Yeah. But you also hinted that even more futuristic tech is in development, and it kind of had me wondering, are we really talking sci-fi stuff here?
It can definitely sound like that, but honestly, the progress in immunotherapy is just mind-blowing these days. Remember those double-headed missiles I mentioned?
Yeah, 2 targets, 1 antibody, right?
Exactly. That's where bispecific antibodies come in.
Okay, so instead of just CD122, we're adding a whole other layer of precision. I'm all for less collateral damage when it comes to fighting cancer, that's for sure.
Absolutely. Less is more in that case. Picture this. One head of the antibody locks onto CD122 on our T cells, right? But the other head, that one's seeking out a specific protein, and not just any protein, one that's only found on the surface of tumor cells.
Oh, wow. So it's like we're playing matchmaker for our immune system. Those killer T cells are going to be laser focused on the tumor cells with that kind of guidance.
Exactly. And by bringing those cells so close together, we're upping the chances of our T cells not just recognizing, but actually wiping out the threat. Think of it like, parking a tank right outside enemy headquarters.
Yeah, no escaping that.
Exactly. They're done for.
And because we're getting so specific with targeting those tumor proteins, does that mean we could be developing even more personalized therapies, like ones tailor-made for an individual's cancer?
You're spot on. This is what makes the potential of CD122 targeted therapy so exciting. We're not just boosting the immune system in a general way. It's like we're giving it GPS directions to tackle each patient's unique situation.
That's incredible. But what about those microscopic delivery systems you mentioned? Was I hearing that right? Are we talking tiny submarines delivering medication inside the body?
It does sound unbelievable, right?
Yeah.
But nanotechnology is opening up some really incredible possibilities. We're not quite at the submarine stage yet, I have to admit. But these nanoparticle delivery systems, they kind of function on a similar principle.
So instead of flooding the whole body with these strong medications, we're using these tiny delivery systems to target specific areas, like right into a tumor.
You got it. Imagine these nanoparticles as microscopic envelopes. And they're carrying a very precious cargo of medication, whether it's IL-2, IL-15, or even those bispecific antibodies we just talked about. The cool part is these envelopes are engineered to seek out and attach to very specific cells in the body. You guessed it, the ones with CD122, those T cells we've been talking about.
Okay, so we're making sure the medication gets delivered only where it's needed. That's got to minimize the risk of affecting healthy cells, which is huge. I mean, this is light years beyond traditional chemo, isn't it?
Oh, absolutely. It's a whole new ballgame.
Yeah.
And this targeted approach comes with huge benefits. For one, it allows us to use way lower doses of medication, which could drastically reduce the chance of those harsh side effects.
Right. We talked about the risk of overstimulating the immune system earlier. This seems like a much more controlled way to do things.
Exactly. Much more controlled. And second, think about it. By concentrating the medication exactly where it's needed, we could make the treatment way more effective. It's all about maximizing the impact while minimizing the damage to the rest of the body. And the really cool part is that we're just starting to figure out what nanotechnology can really do.
It's like we're watching a whole new medical arsenal being invented right before our eyes, and it's infinitely more precise and effective than anything we had before. But with all this incredible potential, what are the next steps? How do we actually get from these groundbreaking ideas to real treatments that help real patients?
That is the million-dollar question for sure. The research is super promising, but to translate that into safe and effective therapies, it takes a lot of really rigorous testing and refinement.
So lots of clinical trials in the future.
You got it. Tons. Clinical trials are going to be crucial for figuring out just how safe and effective these new CD122 targeted approaches are for real patients. We need to confirm that they actually deliver on all this promise, while making sure the risks are minimal. Plus, we need to figure out the best dosages, the best combinations of therapies, and how to keep track of how patients are responding to everything.
It sounds incredibly complex.
Oh, it definitely is, but it's also incredibly exciting. We're talking about potentially changing how we treat some of the most serious diseases out there. And the progress we're seeing in immunotherapy, especially CD122 research, it's all thanks to some incredibly dedicated and smart researchers around the world.
It's really something to think about all those people collaborating behind the scenes to make these breakthroughs a reality, but it makes me wonder if we're already achieving so much with CD122, what else is out there? What other mysteries are hidden within our immune systems?
Ah, that's the question that keeps every immunologist up at night. Honestly, we've only just begun to scratch the surface when it comes to understanding how the immune system works. CD122 is just one piece of an incredibly complex puzzle.
Like discovering a whole universe, but it's inside each of us.
Exactly. And what's so fascinating is that every new discovery just leads to more questions and even more possibilities. It's a never-ending quest for knowledge, but the potential rewards are just enormous.
It's both humbling and really exciting. We're on the cusp of a whole new era in medicine, one where we can potentially use the power of the immune system to do things we never thought possible. It's like living in a science fiction novel, except it's real.
That's a great way to put it. We've covered so much ground on this deep dive into CD122, from the mind-blowing science to the really important ethical questions it raises.
Right, because it's not all sunshine and roses, is it?
Exactly. And speaking of which, there's one more crucial aspect we need to explore: the ethical considerations. With such powerful tools becoming available, we need to make sure they're being used responsibly. That's something we'll dive into in the final part of our deep dive.
So we've been talking about CD122 like it's this amazing breakthrough.
It really is.
Yeah, and it is. But before we wrap up, I think it's important to talk about the ethics of all this, like you mentioned.
Oh, absolutely.
Yeah.
Anytime we're dealing with breakthroughs that could completely change how we treat diseases, we have to think about the implications, not just the science.
For sure. So where do we even start? What are the ethical questions that come up when we're talking about something as powerful as, like, changing the human immune system?
Well, one big one that comes up with any new tech, especially in medicine, is access.
Right, because these therapies aren't just going to magically be available to everyone, are they?
Exactly. Developing these new immunotherapies takes so much research, so much funding, and that often means the treatments end up being super expensive.
So you could have a life-saving therapy, but it might only be an option for, like, the wealthy.
It's a real concern. And it's not even just the cost of the treatment itself. It's also about where you live, whether the hospitals have the right equipment, and doctors who are trained in this new therapy.
Oh, right. So many factors.
Yeah, even just a patient's understanding of their own health can be a barrier.
So it's like this ripple effect. Even if the treatment exists, you need the whole system to support it so people can actually access it.
Exactly.
That makes sense. So access is a big one. What else?
Informed consent. That's always a big deal in medicine, but it's even bigger with experimental therapies. We're
Yeah.
talking about patients who are putting so much hope into these new treatments, so they need to be crystal clear about the potential benefits, but also the risks.
Especially with immunotherapy being such a new field, there are probably long-term effects we don't even know about yet, right?
Right, and that's why it can be so tricky to talk about the risks and benefits. We're talking about complicated science here.
Yeah, it makes my head spin sometimes, even just trying to understand it.
Exactly. So imagine trying to explain all this to a patient who's going through a tough diagnosis.
It's like you need a medical translator on top of everything else.
Yeah, we really need to figure out how to communicate this stuff clearly and compassionately so patients can actually make the best decisions for themselves.
I hadn't even thought about that, but you're so right. And speaking of long-term effects, are there any concerns there? Like, we talked about memory T cells and how they could provide protection for years, but Is there a chance that changing the immune system so much could backfire down the road?
It's the big question, isn't it? And it's something researchers are always looking into. The immune system is so complex, it's not like a simple machine where you can just swap out a part. It's more
We're
like,
trying to reprogram the whole operating system as we go.
that's a great way to put it. We're constantly learning and refining our understanding, which is why it's so important to keep a close eye on patients receiving these therapies. We need to be ready to adapt and adjust as we learn more.
And these ethical questions, they go way beyond just the patient and their doctor, don't they?
Absolutely. For example, who decides which research gets funded? It's not always just about what's scientifically interesting. Sometimes commercial interests come into play. And then there are even bigger questions like, how do we make sure these incredible new treatments benefit everyone, not just a select few?
Yeah, it's a huge responsibility, and it's not something scientists can figure out alone, is it?
Not at all. It really takes a team effort. Scientists, doctors, patients, ethicists, policymakers, even the general public. We all have a role to play in making sure these advances are used for good.
So well said. We've covered so much in this deep dive into CD122, from the amazing science to the really important ethical considerations. If our listeners could take away one thing from all this, what would you want it to be?
I'd say we're just at the beginning of something huge. CD122 research is just one example of the incredible possibilities in medicine right now. But we have to remember that with any powerful tool, we have to proceed carefully and thoughtfully. We need to keep asking those tough questions and working together to make sure these advances benefit all of humanity.
Couldn't have said it better myself. Thanks to everyone for joining us on this journey into the world of CD122 and the future of immunotherapy. Until next time, stay curious and keep those questions coming.